What we did covariance stationary is in chapter 3, but I'm just going to get very specific. Chapter 3, stationary time series. And we are going to start with an MA1 process. MA stands for moving average. The order is 1. I would explain what that order means. What is the definition of MA1? Yt is equal to theta 1 epsilon t minus 1 plus epsilon t. As always, epsilon t is Gaussian white noise. Where the mean equals 0 and sigma squared equals 1. Good. Just like how we try to understand a first order difference equation, second order, third order, eighth order, what we're going to do is understand this model first. Once we get a good idea about what this model is about, we can go back and see how we can estimate the value of theta 1 using that. Does that make sense? So first, our objective is to understand this model. Clearly, the noise will be correlated. Do you agree? So if it was just epsilon t, not a big deal. But what we're saying is this process y sub t involves epsilon t, and what's the random thing that happened, at one time unit before. So since we depend on one time unit prior, this is a first order moving average process. Good. And we call it moving average because we will simply be averaging the noise. When I do the next order, it'll sort of make sense. So let's say if this moving average process is white and stationary, do you believe that it would be white and stationary? Forget about the derivation. Logical deduction, the answer is right there.
Yes.
Why?
Because all you have is epsilon t's.
Okay. Forget about that too. It is under what chapter? Stationary time series. It better be words than stationary. An MA1 process is stationary. But if I did expectation of yt, we will have expectation of theta 1 epsilon t minus 1 plus epsilon t. I can distribute, so theta 1, epsilon t minus 1 times theta 1 expectation of that plus expectation of epsilon t. We know the expectation of epsilon t is 0, so that would become 0. Theta 1 is a constant. that would become 0. I mean, may it be time t or time t minus 1. The expectation of the epsilon for anything is 0, so we will get 0. Expectation of that is also 0. Good. Next, we have to find the covariance of yt, yt plus h. One of the key things that we have to sort of understand when we do covariance and such, or trying to find the covariance, is something called index matching. I call it index matching. So what are the terms, which would have identical time indices for some value of h, are the only terms that would show up. Everything else would become 0. Right? So if I could match this with that, sure. Let's start with h equals 0. If h is 0, would that term and that term match up?
Yes.
Yes. So gamma of 0 will be covariance of theta 1 epsilon t minus 1 comma theta 1 epsilon t minus 1. Correct. Because this time index and that time index would match. If h is 0, that and that not going to match. Correct. If h is 0, that and that not going to match. If there should be one. If that is 0, that and that will match. So covariance of epsilon t, comma epsilon t. I have a theta 1 here, I have a theta 1 there. If I pull those two out, I'll have theta 1 squared. Covariance epsilon t minus 1, epsilon t minus 1, plus covariance of epsilon t, comma epsilon t. What is the covariance of epsilon t minus 1, comma epsilon t minus 1?
0.
So that would be variance of epsilon t minus 1 plus the variance of epsilon t. Yes? What is the variance of epsilon t minus 1? 1. Let's generalize this. Let's not put 1, we'll keep it as sigma squared. Variance of epsilon t is also sigma squared. So we will have 1 plus theta 1 squared multiplied by sigma squared. What did we just find? We found, can I erase this? Covariance of yt, h is 0, comma yt, which I denoted as gamma sub 0. But what is covariance of yt, comma yt?
The 1 plus theta 1 squared times sigma squared.
I agree, but what is it called? Variance of yt. So variance of yt, which would be 1 plus theta 1 squared multiplied by sigma squared. Good. And now I would like to find gamma 1, that is when h is equal to 1, gamma 1 is simply covariance of yt, comma y, t plus 1. Yes? Use the same process and tell me if you can find the covariance of yt, comma yt plus 1. So we're going to set h is equal to 1. Okay, let's use that in this matching technique that I talked about. You don't have to write them all up. So the only time the covariance is going to exist is when the index matches. So h is equal to 1. That would mean here it would become epsilon t, right? Let's write that part out so that we don't make mistakes. Yes. So got too excited there. Okay, are we okay now? So the index doesn't match there, so I don't care about that term. Index doesn't match there, don't care about that term. Index matches there, so I'm going to stick to that term. That term. So covariance of epsilon t, comma theta 1 epsilon t. That's not. Index doesn't match, so I don't care. So there is a constant out, so I can pull theta 1 out, which will give me covariance of epsilon t, comma epsilon t. But what is covariance of epsilon t, comma epsilon t?
You pull D1 out even though it's only one of the.
Come again.
You can pull D1 out even though.
Theta 1.
Theta 1, even though it's only one of the. Not sure what I was saying.
Okay, let me know when it comes to you.
They give epsilon t and theta 1 epsilon t. And you can just pull out the theta even though it's only attached to one of the epsilon t's.
Yeah, if there is a theta 1 here and a theta 1 there, like the previous case, it would become theta 1 squared. Right? Here it's just theta 1. So that would equal to theta 1 multiplied by the covariance of epsilon t, comma epsilon t. What is the covariance of epsilon t, comma epsilon t? Variance of epsilon t. And we know what the variance of epsilon t is, that is sigma squared. Right? In a similar manner, we can find gamma 2. But is it necessary? Why not?
You already know that, because you've already done the case 1 example, like it's always the constant. You have the 0.
But why not gamma 2?
Why do you have to?
Well, there has to be a reason if you say no. I mean, nothing will match with each other. Very good. Nothing's going to match when you put t equals 2. No term would match and you simply get 0. That is the mathematical explanation. But if you had to look at it intuitively, what we're saying is, sure, YT is correlated or expressed in terms of epsilon t's, but those noise components can only be correlated by a lag of 1, right? This means correlation at a lag of 2. That's not going to happen, correct?
Would it need to be order 2 for that to work?
That is correct. For order 2, this would not be 0. So I can generalize it and say a 0 for k greater than or equal to 2. Good. So we found gamma naught, we found gamma 1. Beyond that, things would just be 0. So the covariance function for an MA1 process I should say autocovariance function. Gamma h is equal to 1 plus theta 1 squared sigma squared, or h is equal to 0. Simply theta 1 sigma squared, or h is equal to 1, 0, otherwise. Good. We have the autocovariance, so how do we find the autocorrelation? You can look in your notes. You should know this. If you recall, we said just because the covariance is large doesn't imply that you have a strong relationship, right? That's something that we addressed when we were talking about covariance, which is why we did correlation. The autocorrelation function is simply the autocovariance function divided by the variance. So in this case, we want to take theta 1, sigma squared divided by 1 plus sigma squared, theta 1 squared times sigma squared. When h is equal to 0, you have gamma of 0 over gamma of 0, correct? Which is 1. So the autocorrelation function is always 1 when h is equal to 0. Don't forget that. But does it make sense intuitively? If you are correlating with yourself, it better be 100% correlation, right? If a variable is correlated with itself. So it's always 1. But when h is equal to 1, we will take theta 1 sigma squared divided by 1 plus theta 1 squared. And that's what we would have, and 0 otherwise.